Welcome to Lecture 6. Today we will be covering balanced forces. So this is where we're kind of getting into some of the fundamental concepts of the Newtonian formulation of mechanics. So a force it's a bit hard to define, but think of it as an interaction. And an object can be acted upon by a force, and sometimes it can exert forces on other objects. So over here we have this formula, F equals ma. Notice that F and a are both vectors, and this means that force is equal to mass times acceleration. So if an object has a force on it, then it will accelerate. And if an object does not have a force on it, it'll not accelerate. And technically this should say F net is equal to ma, because if two forces balance each other out, say I'm pushing on an object to the left and I'm pushing on it from the right, if I'm pushing on it from the left and from the right, then the object won't move if I'm pushing with equal strength, because those forces balance each other out. And they add using vector addition. Let's say that when I'm pushing from the left, that's a force of I hat, and when I'm pushing from the right, that's a force of negative I hat. That adds up to 0. So there's no acceleration. And again, if an object isn't accelerating, then it's either at rest or at constant velocity, as we said back in the kinematics lectures. And yeah, so that's the important thing to know about forces, is that if there's an unbalanced force, it'll cause an object to accelerate. And in the SI convention, we measure forces in newtons, which are kilograms times meter per second squared. You can see how we got this. Mass has units of kilograms and acceleration has units of meters per second squared. So here's some kinds of forces that are kind of difficult to think about and that are also pop up a lot in different physics problems. So you have Earth's gravity, normal force, tension, and friction. So let's start with Earth's gravity. So on the Earth, gravity has a magnitude m times g, where g is acceleration due to gravity, 9.8 meters per second, and m is the mass of the object, and it always points straight down. So right now, I'm sitting in a chair. There's a force on me. I'm not going to say how much I weigh, but it's my mass times the acceleration of gravity, and it's pointing straight down toward the center of the Earth. And so this gravity is pulling down on every object on the Earth. And technically gravity is not given by mg for everywhere, but at the surface of the Earth we can use the approximation mg to substitute for the more accurate Newtonian formula for gravity, which we will cover later in this course. So another type of the force is the normal force, which is exerted by a surface on an object that the surface is supporting. So like I said earlier, right now I'm sitting on a chair. The chair is exerting a normal force to stop me from falling through the chair. So the normal force is perpendicular to the chair. That means that it's pointing straight out of the chair, not along the chair. And it doesn't really have a set magnitude, but it cancels out any force in the same direction. So like I said earlier, the force of gravity is pointing straight down, right? And the normal force is pointing straight up because my chair is flat. So the normal force is large enough to cancel out the force of gravity, and no larger, no smaller. If it were larger, then I'd be pushed out of my chair, but that doesn't happen. And if it were smaller, I'd be sinking into my chair, and that also doesn't happen. So another kind of force is tension, which is exerted by ropes. Tension and the normal force are both kind of inscrutable because they don't have any set magnitude, and tension especially can be a bit confusing because it's hard to see the direction and the magnitude of the force. So tension, we will talk more about tension later in this course, but right now all you have to know is that it's exerted by a rope in the direction along the rope from the end of the rope to the middle of the rope. So the rope kind of pulls objects in. And the reason why tension points in this direction is that if it didn't point in this direction, then the rope would be distorted. It would be pulled by its own tension force, which is something that doesn't happen. And tension corresponds to a big class of force problems, and a lot of thinking is required to treat problems with tension, and we will go into depth with that later in this course. Now, the last special kind of force we'll cover here is friction. Let's say I'm sliding down a hill. If it weren't for friction, I'd just accelerate down the hill because of gravity and the component of the normal force that is pointing horizontally. And when I say the component of the normal force that points horizontally, I mean that the normal force points straight out of the hill, right? It doesn't point up. So there's a component of the normal force that points up and a component that points forward, from my perspective. And that's something important to understand about the normal force. Anyway, so friction is equal to this coefficient mu times the magnitude of the normal force, and it points parallel to a surface. So, more specifically, when I'm sliding down this hill, the force of friction points upward toward where I came from, because it is decelerating me. The way I feel it, I'm moving downward, and I feel the friction force pushing me upward. And that's the direction that the friction force is pushing in. Now, mu is the coefficient of friction. It's between 0 and 1. 0 would be for like a very slippery surface, think, the smoothest ice. And 1 would be for the most frictiony surface. Yeah. So it can be different for static and kinetic friction. Static friction is like, let's say I'm sitting on the hill, but I'm not sliding down, that's static. And if I'm sliding down, it's kinetic. And usually static friction has a higher coefficient than kinetic friction. All right, now we're going to go into free body diagrams. Like I said earlier, I believe in lecture, was it 5? No, it was 4. It's important to draw a diagram to give yourself a spatial conception of a problem. So basically what a free body diagram does is it allows us to graphically represent an object and all the forces acting on it. So we'll draw the object as a point, and then each force is an arrow that points from the point outward. So the length of the arrows is proportional to the magnitude of the force, and of course they point in the same direction as the force. And note that it might be a bit difficult to draw a free body diagram for 3-dimensional problems, given that paper is 2-dimensional, but you shouldn't have to deal with this too often. And let's go on a quick aside about how to balance forces before we get into today's example problems. So forces are vectors, and we can break vectors down into components in the I hat, j hat, and k hat directions, or in whichever vector basis we're using. And so, to balance forces, we need the components of each force to add up to 0. The components of each force in the same direction to add up to 0. So what we can do on the free body diagram is we can draw our x and y axes, and then split up, we can break down our forces using the Pythagorean theorem into their components on the x and y axes, and then we can balance those individually. All right, example 1. We have a 1,000-kilogram car sitting at rest on a frictionless slope inclined 30 degrees to the horizontal and tied to a rope that points up the slope. And let's find all the forces. So I'm going to start drawing a free body diagram here. First, let's draw our slope. Technically, you don't need to draw this in the free body diagram, but I find it helpful so that I know what I'm dealing with. And this angle is 30 degrees. And now let's draw our car. I am not going to waste any time drawing anything that looks like a car. Instead, I'm just going to use this big magenta dot to represent the car. And now let's look at each individual force. So first, let's start off with gravity, because that's the easiest one, because we know its magnitude. So the magnitude of the force of gravity on this car is its mass, 1,000, times the acceleration due to gravity, 9.8. That is 98. Oh, we have a text option. Let me use that. That is not working. Okay, there we go. 9,800 newtons. All right, next up we have the normal force, which points directly out of the page. And we don't know the magnitude of the normal force, but so what I'm going to do is I'm just going to draw a headless arrow here, and we'll extend this arrow later. And then lastly, we have the tension force. I guess I didn't specifically specify this in the problem, but we're going to assume that this rope is parallel to the slope, and so the tension force goes this way. So now we have forces pointing in a bunch of different directions. And we have two options for how we might want to break down this problem into components so that we can balance the forces. First, what we could do maybe is break down each of these into x and y components, where we have, here's the y direction, and here's the x direction. But that doesn't seem like the best idea here. And the reason why is that, the reason why is that these two forces are perpendicular to each other. So we can use them to make a perpendicular basis. So we'll have, that's a bad diagram, but like this and like this, where this guy is 30 degrees to the x-axis and this guy is, 120 degrees to the x-axis. And I will draw with bad dotted lines our x and y axes. So thinking about this, we can now break gravity down into its constituent components. And I guess I used dotted lines here, but I'm going to use a gray for these components. So, okay, that is not visible. What if I use a green? There we go. So that is one component, and this is perpendicular to the surface and directly parallel to the normal force. And here's another component. And this is parallel to the surface, and it opposes the tension force. And so we know that the forces in this direction, if you can see my mouse gesturing, I'm going perpendicular to the surface, have to add up to 0. So that means that our normal force has the same length as this arrow here. And now we have to use some geometry here. So let's do some geometry. This angle is a 30-degree angle. I guess the way to see this is that this is a right angle here. This is a 60-degree angle because this is the 30, 60, 90 triangle. But yeah, you should be able to angle bash that by yourself. So this is a 30-degree angle, and we can draw a 30, 60, 90 triangle here between these two rays. And this is 98,000 newtons. The text label needs to move. Nothing I can do about that, unless there is. All right, that's helpful. So this is 98,000 newtons, and we know from our 30, 60, 90 triangle formula that this would have to be 49,000 root 3 newtons. Alternatively, the cosine of an angle is equal to, come on, I can remember this. Cosine is equal to adjacent over hypotenuse. Cosine of this is equal to root 3 over 2, so this over this is root 3 over 2, so this has to be 4900 root 3. I'm not going to flesh out the geometry again, because it's nasty stuff. But anyway, this is 4900 root 3 newtons. And then, of course, we know that this guy is the opposite, so he has to be 4900 newtons. And I'll drag it a bit. Alright, so now we know that this tension and this parallel component of gravity have to cancel out because there are no other components in that direction. So let's delete this guy, and we will draw it again with the same length. This is the force of tension. Oh, I guess I haven't been naming these. This is force of gravity. We'll write it F sub g. And then these are its components, which I don't need to label. This is the force of tension. I'll label it F sub t. And this is the normal force. I'll label it F sub n. That's legible. And then again, F sub n has to cancel out with the perpendicular component, and F sub g has to cancel out with the parallel component. So these guys' magnitudes are 4900 newtons and, come on, 4,900 root 3 newtons respectively. All right, so that is our first problem. Okay, example 2. Or I will deselect these because it's really much the same. So now we're cutting the tension and replacing it with friction. And what we want to do is we want to find the coefficient of friction. So because the problem setup is really basically much the same as the last time, we know that all these forces are the same, we know that this normal force is the same, and we know that this guy has to be the friction force. Remember that the friction force points upward to cancel out the downward, well, up the slope to cancel out the down the slope component of gravity. And so I will mark this as F sub F. And as we know, it has to be 4,900 newtons. And remember that, I guess I didn't write this out fully, but F sub F, that should be an F, is equal to mu F sub N. And then substituting in our numbers, we get that, and I'll ditch the handwriting now because I can use the text. 4,900 is equal to mu times 4,900 root 3. And so by basic algebra, our mu is equal to 1 over root 3, which is equal to root 3 over 3. And note that mu is dimensionless because we're converting newtons to newtons. All right, so that is our second example, and that is the end of the lecture. I will try to churn out a supplemental to go with this lecture because we went pretty fast over a lot of concepts. But yeah, thank you for watching.